All right, so welcome everybody. I'm very pleased to see such a large number of people here for what is the inaugural, hopefully first of many, Applied Networking Research Workshop, which is being organized by SIGCOMM, the IRTF, and the Internet Society. I'm Colin Perkins, one of the workshop program chairs. Lars Eggert, the other co-chair, is at the front with me here. So the goal of this workshop, we're aiming to try and provide a venue where the research community, vendors, network operators, people in the internet standards community can come together, where we can try and get some discussion, some interesting early results, some very applied networking research, and try and see if there's any synergies, try and see if we can bring new research work towards the standards community, the vendor community. The goal, hopefully, is that the results of some of this discussion can maybe inform future work in either the IETF, the engineering, the standards process, or in the research community with a view to sort of longer term, sort of bringing things into the standards process. So we're really trying to get the research community, the standards community together, try and bring some of the research ideas into the standards process, see if any of them are ready for actual standardization and deployment. So we're very pleased. This is a peer-reviewed workshop. We're very pleased by the response. We got a total of 30 submissions, which I think was excellent for the first workshop of its type, of which there were 17 full paper submissions, 13 short papers. Each of the submissions was reviewed 3 times by the TPC members. We got some exceptionally detailed reviews. Some of the TPC members, I think some of the short papers got reviews that were almost as long as the paper. So I very much appreciate the effort that the program committee spent on some of these. In the end, we accepted 9 of each, 9 full papers, 9 short papers. All of these are available on the workshop website. They're available open access on the website. They've been up for a few days now. They're also on the ACM digital library, and that is they're actually up on that site, and they should be open access on the ACM digital library site as well. Very much want to thank the program committee. And I'm not going to read the names out, but we have a long list of people who volunteered their time to review the papers, and as I say, put a tremendous amount of effort into this. And we very much appreciate that. Also the other steering committee members, Lars, Matt, who's on the registration desk, Jörg, and for just putting a tremendous amount of work into the logistics and making this work. And also, by no means least, I want to thank the sponsors, Akamai, Cyclops, NetApp, ACM, SIGCOMM, the IRTF, and the Internet Society, who've contributed a tremendous amount to sort of making this workshop a success.
Say something about the travel grants that we use.
And travel grants, of course, yes. We have, I don't know how many of them are here, but we made a number of student travel grants, and again, due to the very generous sponsorship of these people.
6 or 7.
6, I think, yeah, something like that. So hopefully some of those people are here, and please come and introduce yourself if you are a travel grant recipient. So, our agenda today. We have a bunch of sessions, breaks in between. The lunch break and the afternoon break will be poster sessions. If you have a poster, please put it up during one of the breaks, and so we'll have the discussion of the posters over lunch and in the afternoon. Following all of this, there is a social event at Freie Universität. If you wish to go to this event, you need to register. It's free, but go to this website and sign up if you haven't already. And this is part of the Riot Summit, which is also happening today. But please go along. There's a barbecue. Should be fun this evening. In terms of the papers, we have 2 types, full papers and short papers. If you have a full paper, we're expecting about 20-25 minutes presentation, 5 to 10 minutes questions in a 30-minute slot. If you have questions for clarification, please ask them during the talk, discussion at the end of the talk. We have microphones, we are being recorded and live streamed, so if you want to ask a question, grab one of the microphones. I think there's one at the back, and I'll hand this one around as well. If you have a short paper, short papers, you have 5 minutes for presentation. No exceptions whatsoever to this. Right? When the short papers are happening, if the speaker is still talking after 5 minutes, we're going to start clapping. And we're not going to stop until the person stops talking and sits down. So these are absolutely no questions, absolutely hard cut off after 5 minutes.
Yeah, the idea is that your short paper talk should be an ad for your poster,
yes.
Right? So that's why there's no discussion. The discussion will happen around your poster and the breaks.
Yeah. Otherwise, a couple of bits of administrivia. We are being recorded, we are being live streamed. The live streaming should be working via that URL. The live streaming asks you to accept the IRTF Note Well and intellectual property regulations. None of that actually applies, it's just an artifact of how the live streaming is being done. So don't worry about that, just ignore that. But I think you have to sign up to it, but it doesn't apply. Equally, this is organized by the IRTF, but the IRTF intellectual property rights disclosure rules do not apply in this workshop because this is a SIGCOMM, ISOC, etc. workshop as well. Okay, so before we get started, just a couple of questions. Just try and gauge who's who in the audience. First of all, anyone here who's never been to an IRTF meeting before? Okay.
No, 15 maybe.
Keep your hands up. Okay, a dozen maybe, yeah, okay. That's pretty good, thank you. Well, I'm glad you're here. Are any of you planning on sticking around for the rest of the week, or at least some of the week? A couple?
No, of the ones.
Of the ones who have never been. Well, I mean, the ones who have attended IRTF. Is anyone coming for the rest of it, or are you all just leaving? Maybe with a big draw. So if the people who've never been to IRTF before, how many are sticking around? Okay.
4, 5, 6.
5, 6, about half of them maybe. Okay, good, good. And finally, how many students do we have? So, okay,
It's pretty
15,
good.
20. Okay, yeah. Good, good. So I do hope you will get something out of this workshop. If you're sticking around for IRTF, I very much hope you will get something out of IRTF. IRTF is an interesting experience. I hope it will be a beneficial one. I think Lars is going to say something about what standards at the end.
Yeah, so we have a little session at the end where we're going to have a discussion about how does this go, how can we make the next one better. This mic is way hotter than your mic. The other thing I was going to say is that so this is a workshop, right? It's not a conference or something where you sit there and you're being talked at. You should really ask questions, right? Especially the students, if they are, if you have questions about the talks, right? If the presenter is unclear, go to the microphone and ask them to explain themselves. If you have a comment, like a longer discussion, go to the microphone and discuss, right? If we're all sitting here and nobody asks any questions, I will be very disappointed. I know I don't have to encourage the normal IRTF people to do this. to the IRTF people, I maybe want to say, let the students maybe have a first dip at engaging in a discussion, right? If anybody who has any dots on their badge should always go to the back of the queue today. All right, I know your dots. And in the spirit of questions, is there any questions about what Colin and me have sort of laid out so far, how this is going to work today? Yeah, so Matt says there's going to be a mic stand sort of in the aisle there. So if you want to ask questions, go to that mic, and it's probably going to be the one that Colin is currently holding.
We'll just pass this mic around for now.
Yeah. Okay.
Well, in that case, the agenda for the first session is up on the screen here. Do we have someone for the first paper? Or does this grind to a halt very quickly? We will time the short papers. Yes.
Does anybody have one of those remote clicky thingies for the presenter? Because I think that would be useful, since I guess the microphone indicates that the streaming people would like the speaker to stand over there.
So the first paper is entitled An Enhanced Socket API for Multipath TCP. So most of the work has been done by Benjamin Esmant, and I will serve as a backup presenter since Benjamin is on holidays. He has something more important to do this week. So the outline of the talk is that I will try to explain you what is multipath TCP, and then I will explain you how we can design an API, a socket API, to control the operation of multipath TCP. So multipath TCP, for those who are not aware, is a recent extension which has been standardized by the IRTF about 2 years ago. And it's an extension of TCP that allows to send packets over multiple paths that belong to a single TCP connection. And multipath TCP has several use cases until now. So with multipath TCP, it's possible to create a TCP connection and send data over both Wi-Fi and LTE, either together or one after the other in an handover scenario. It's also possible with multipath TCP to create a connection over IPv4 and then create a second part of the connection over IPv6 and send data over both IPv4 and IPv6 in a dual stack scenario. And there has been a use case with multipath TCP doing equal cost multipath in data centers by exploiting the diversity that exists inside the data center. So multipath TCP was designed as an evolution of TCP. It's not a revolution like SCTP. We try with multipath TCP to have something which can be incrementally deployed on the internet. And the design objectives of multipath TCP, when multipath TCP was designed, the three main objectives were that multipath TCP must support unmodified applications. It must work over today's network, so it means that it must operate over IPv4 and IPv6. And the last design objective, which turned out to be the most difficult one, is that multipath TCP must work in any network where regular TCP works. And any network, initially, we thought that it meant IPv4 and IPv6. Over the development of multipath TCP, we found that any network means that we have to take care of all the middle boxes, and it turned out to be a pretty messy scenario, but we managed to do it with multipath TCP. So if you look at multipath TCP in the reference model and how it fits in the reference architecture, so you have the standard application. Since we want multipath TCP to work with unmodified application in the current version of multipath TCP, we do not change anything to the socket layer. So the application still interacts with multipath TCP with the regular socket interface. And multipath TCP is in fact a way to glue multiple TCP connections together. And multipath TCP is the glue between these different TCP connections, and the different TCP connections, which are called subflows in multipath TCP. They are used to carry the data and to transport the data over the different paths that exist. And a typical deployment of multipath TCP on smartphones, for example, means that you would have one TCP connection which is operating over the cellular interface, and one TCP connection which is operating over the Wi-Fi interface. And multipath TCP would combine these two subflows together so that you have the illusion of having a bonded capacity between LTE and Wi-Fi over your smartphone. So multipath TCP was standardized 3 years ago now. And before looking at how it works and how you can use it, it's interesting to look at what are the current deployments of multipass TCP, and there are three main deployments today of multipass TCP. The first one was from Apple in September 2013. So Apple has a small application which is called Siri, which is getting more and more importance over the Apple devices. So that's a voice recognition application, and typically Siri works by capturing voice on the smartphone and then sending voice to a cloud server, and the cloud server will contain the intelligence and send the feedback to the Siri application. And to make the application work correctly in all scenarios, it's important to be able to send data over one of the paths, for example, the Wi-Fi, and be able to quickly retransmit the data over the cellular interface if the Wi-Fi fails. And Apple found that the best way to do this kind of handover was to use multipass TCP. So since the last 3 years almost, we have a huge deployment of multipass TCP for one application, where multipass TCP is running on the iOS devices and multipass TCP is running on the servers that are maintained by Apple. And this goes through the regular internet and through most cellular networks correctly. Second deployment that was announced last year, if I remember, in Korea, the smartphone users in Korea, they expect to have huge bandwidth available. And the way to get huge bandwidth is to improve the quality of LTE. So they are getting about 300 megabits per second over LTE, but this is not sufficient. So they want to combine this with fast Wi-Fi, which means Wi-Fi at 600 megabits per second. And if you can combine them together, then you have about 1 gigabits per second for the smartphone users. And they do this by using multipass TCP on the smartphone and by going through SOC servers that are maintained by the network operators. And there are currently 3 network operators that are doing that in Korea. And we expect more in the coming years. A last use case, which is being developed by several operators and several companies, is the idea of hybrid access networks. Hybrid access network is the idea of combining DSL and LTE together, and you combine DSL and LTE through a specific hybrid access gateway. And again, you are using multipass TCP to do the combination between the LTE network and the DSL network, and the hybrid access gateway will convert multipass TCP to regular TCP so that you can interact with servers that have not yet been upgraded to support multipass TCP. So with multipass TCP, we send data over multiple paths, and to send data over multiple paths, due to the existence of the middle box on the internet, what we had to do is that multipass TCP, a connection, is composed of one or more regular subflows, and these subflows are combined together, which means that on the sending host and on the receiving host, you have some state that glues the different TCP subflows together. And a subflow that you send over one path appears to the routers and the middle box that exist in the network like a regular TCP connection. And this is very important for the incremental deployment through firewalls, through NATs, and all the different types of middle boxes that we have. So let's look quickly at how we can create a multipass TCP connection. And then once we have created a multipass TCP connection, we can create a subflow, a second subflow. So we will have a smartphone, and this smartphone is connected with 2 interfaces, a blue one and a green one. And let's assume that the blue one is the default interface. So when we create a connection to a multipass TCP enabled server, we will create the connection over the blue interface. So this is done by using a 3U handshake. And in the 3U handshake, there is a special option which is called multipass capable. And the multipass capable option contains an information which is a key that will be used to authenticate the establishment of subflows. But the key is also used to create a token, and the token is the local identification of the multipass TCP connection on the host. So there is a token that identifies the multipass TCP connection on the smartphone. And from the key which is generated by the host, we derive the token which is known by the server. The server selects its own key and thus its own token as well. It accepts the connection, the establishment of the connection by sending an MP capable option with the key of the server. And then the smartphone confirms the establishment of the connection. So we have the multipass TCP connection which is established. We can send data over the multipass TCP connection. And multipass TCP will allow you to send data over any of the subflows which is available. And to do that, we have two levels of sequence number, the regular TCP sequence number and the multipass TCP sequence number. And this will allow you to retransmit data over another subflow than the original one. So at this point, we can send data over the blue interface. The next point is to be able to transmit data over the green interface. To be able to transmit data over the green interface, we need to create a subflow over the green interface. So for example, the cellular one, this is done by using, again, a three-way handshake. And this three-way handshake will contain a different option, which is the multipass join option. And the multipass join option contains a token, which is the identification of the multipass TCP connection to which the subflow below, and some nonce to be able to authenticate the establishment of the subflows thanks to the keys that have been exchanged at the beginning of the initial multipass TCP connection. So we do the three-way handshake, we authenticate the subflow, and once the second subflow has been established, we can send data over any of the available subflows, and we distribute the data over the different subflows. So what is a subflow? A subflow is any TCP connection that we can create between the client and the server, and they just need to differ by the source IP address, the destination IP address, the source port, or the destination port. So if they differ by the client address, this would be the case when the smartphone is using Wi-Fi and LTE. They can differ with the remote address. For example, if the server is having multiple IPv6 address, or you can have difference in the port numbers. And with MPTCP, in theory, you can support any management of the subflows, and it's possible for a connection to have multiple subflows that exist at the same time or that exist in sequence for a given TCP, for a given multipass TCP connection, and we've seen that in measurements with smartphones. So then the question, once you have multipass TCP, how do you control the subflows? So then I will discuss two options that exist. The one is on the Linux implementation. So on the Linux implementation, the socket API has not been modified. So how do you control the subflow? The control of the subflow is done by a path manager, which is a kernel module. And currently, there are two kernel modules that have been implemented. The first one is called the full mesh. And what the full mesh path manager does is that it tries to create a subflow every time there is an address which is known on the client or on the server. So every time there is a new IP address which becomes available on one of the communicating hosts, it creates a subflow over this interface. So this corresponds for the smartphone case. As soon as you get to a Wi-Fi network, you will create a subflow over this Wi-Fi network for each multipass TCP connection that you have. The second kernel module is called NDIF ports, and it was designed for data centers. And the idea is that we create multiple subflows with different source ports on a given interface, and it's mainly used for data centers. And when the first implementation of multipass TCP was done on the Linux kernel, the idea was that people could implement different path managers as different kernel modules to adapt to their use case. In the end, it turned out that implementing a kernel module was very difficult and nobody did it. So nobody implemented a new kernel module to have an application which is better adapted to the utilization of multipass TCP. There is another implementation which is more widely used, which is the iOS implementation or the macOS implementation from Apple. This implementation is not officially documented, but if you look at the source code which is released by Apple, you will see samples of source code that uses multipass TCP. And the way Apple uses multipass TCP, likely for Siri, is that they have created a new address family. So you need to use the new address family to be able to create a multipass TCP socket. And once you have created this new address family, you can use new system calls. So this is the connectix system call that you probably know from SCTP. And they have designed a specific structure that allows you to create the establishment of the subflows over a given multipass TCP connection. So you can add or remove subflows by using specific system calls on Apple devices. So now let's look at how we can build a socket API to allow the application to control the utilization of multipass TCP and mainly the utilization of the subflows. So we will be doing that by using socket options. So why do we do that with socket options? because socket options are well known by application developers, so it's easy to use socket options. It's also pretty easy to implement socket options, the support for socket options in the kernel. And socket option allows application to pass information as a memory buffer to the stack and also retrieve information as a memory buffer to the stack. This is a bit hacky, a bit ugly from an implementation viewpoint, but it allows you to pass opaque data, which means that we have the ability to interact with any type of information we want with the stack. So the MPTCP socket options that we have implemented right now are the following one. So we can retrieve the IDs of the different subflows. We can retrieve the endpoints of a given subflow, so which is the equivalent of get peer name over a regular TCP connection, and then we can create, close a subflow, a specific subflow. And also we have the ability to set or get a specific socket option on a specific subflow. So for example, on Linux, you have the TCP info socket options that allows you to get statistics about the operation of the TCP connections, like the round trip time, the number of retransmissions and stuff like that. You can apply it on a per subflow basis with MPTCP if you want. So a few examples, very short examples. If you want to retrieve the list of the currently established subflows, because the subflows can be created by the client or by the server. So when you are a multipath TCP application, you don't necessarily know how many subflows are used at a given time because you are not necessarily responsible for the establishment of the subflow. So if you're on the server side, the subflows might have been created by the client. And if you want to check how many subflows there are, you can do that by retrieving this information. So we have a special structure that allows to catch this information. And you use MPTCP get sub IDs, and it returns a list of the subflow IDs, and each subflow is identified by an identifier. And this identifier will be used later on if you want to apply a socket option or if you want to close a given subflow. You can also do the equivalent of get peer name to retrieve the endpoint, the source IP address and the destination, the local endpoint and the remote endpoint of a given subflow, provided that you know the ID of the subflow. So you have retrieved first the ID of the subflow, and once you know the ID of the subflow, you can use that to retrieve the endpoints of the subflow. And if you want to create a subflow, this is pretty easy as well. You create a memory buffer which is large enough to contain the address of the source of the local endpoint and the remote endpoint and the subtuple structure. You fill the local endpoint, you fill the remote endpoint, and once you have filled the data structure, you pass the information to get socket option, and it will create the subflow that you want over a specific interface or over a specific path with the control of the path that you have. So to summarize what this socket API for multipath TCP brings is that it's clear that multipath TCP is getting deployed. So today, the deployment is mainly for one specific application with Apple and on middle boxes. But looking at the discussion with the users of multipath TCP, we often get questions, how can I do that? How can I do that as a specific application? So there is a demand to have applications that are multipath TCP enabled and where you can have more control of the underlying stack from the application viewpoint, mainly on smartphones. So with that, we will be able to do more and more multipath TCP end-to-end compared to multipath TCP between middle boxes. So we have a better interaction between the application and the underlying MPTCP stack. So we can already create, delete query subflows and apply options. And this is already running. The next step is that we are working on non-blocking I/O and the support of events. So events would be important because on the multipath TCP connection, you might lose a subflow at a given time, and the application would like to be able to know that one subflow has been lost without having to poll the MPTCP stack all the time. So this can be done by using receive message and send message over the Linux implementation. We are also implementing the address management. So in multipath TCP, you have the add address option and the remove address option that allows to advertise new addresses from the server side or from the client side, or stop the advertisement of addresses. This information can be passed to the application, And it's also possible to define specific options to control the stack. For example, there are multiple schedulers in multipath TCP. So it's possible to write a socket option that would allow an application to specify a given scheduler for a multipath TCP connection based on the needs of the application. And finally, we are looking for cooperation with application developers. So if you are developing applications that could benefit from multipath TCP and would like to test our multipath TCP code, or would like to work with us on improving the multipath TCP code so that it better supports your ideas as an application developer, come to us. There will also be discussion at the IRTF on Wednesday on the socket API, because we would like to have a common socket API for the different multipath TCP implementations that already exist. With that, I think I'm done.
So questions, we don't have a mic stand yet, but I think Matt is passing the mic around. And please remember to say your name.
Okay, Jörg Ott. Yeah, one quick question. Socket API has always been a bit of a tricky thing to use. Did you do any, when you do extensions to it, did you look into any usability studies of some sort on how easy or how difficult it is to include this in two applications? I didn't see any assessment of or motivation. This seems like, okay, this is a design that can work, but how well does it work? Or is this the last bullet on that last slide?
So that's the last bullet. So we are now working with students, and the students will port some applications over multipath TCP so that we can see whether the abstraction that the socket API provides is sufficient for the application developer. And if not, maybe we'll use the socket API as a low-level interface between with the stack, and then we'll have to build on top of that a library that allows to abstract some information. For example, the management of the addresses is something which is a bit tricky, and the question is whether which part must be placed in the kernel and which part must be placed in the application. And at this point, it's not totally clear, so we like to do experiments with different applications to understand what are the real needs of the applications.
Okay, good. Great to hear that this is not the last word.
No, this is not the last word. This is the first word.
Hi, hello, I'm Avinash. One of the goal of multi-part TCP is...
Could you speak more into the mic? We can't really hear you.
One of the goal of multi-part TCP is if both ends could not find multiple paths, they should use a regular TCP. So how you incorporated in your APIs?
Okay, so one of the goals of multipath TCP was that if you could not use multipath TCP, you would fall back to regular TCP. So if you fall back to regular TCP, then the socket options for multipath TCP will return an error that will tell you that the multipath TCP connection has fallen back to regular TCP, and then the standard system calls for regular TCP would apply. So if you try to apply a multipath TCP specific socket option on a TCP socket, then you would get an error that tells you that you have got a fallback to regular TCP.
Please wait until you have the mic, because we're being streamed. It also would help, I think, Matt, if people with questions come to the center aisle and just, unless you feel like you want the exercise.
I also think there's a second mic.
Matt is running every ITF.
Varun Singh, I had a question. I didn't see any API about coming to know if there's a new socket, a new path available, like asynchronously. For example, like something disappears or something appears, how would the application actually know?
So currently what we have, but which is not in the paper, is that we have extended receive message and send message so that you can use the receive message, the additional data, the control data that you can receive with receive message and send message. So you get additional data that will tell you that there is a new subflow that has been established.
Okay.
So that's a way to get events from the kernels. But there are probably other ways to do that. So for example, there was a discussion last week, there was an email from Apple saying that it would be nice to use KQ to be able to provide events from the stack to the application. So we'll see what's the best option and which solution works best.
Okay.
I'm Rona. Can we make a normal TCP to be a MPTCP soft flow in the middle? Like, yeah.
What do you mean by?
So currently we have a normal TCP, and during transfer, I want to make it a part of MPTCP soft flow.
So you start a connection with a regular TCP?
Yes.
And you want this TCP connection to be upgraded to multipath TCP?
Yes.
So currently this is not possible because you have to negotiate multipath
yes,
TCP
I
at
agree.
the beginning.
Yes, but is that is it a good idea to do, or not? Any incentive or?
But the issue will be the middle boxes. So if you start with regular TCP, you might be in a situation where there is a TCP proxy on the path. And if there is a TCP proxy on the path and you try to upgrade it to multipath TCP, you will have strange issues. So it's better to try to negotiate multipath TCP at the beginning. And once you have negotiated multipath TCP at the beginning, you can use multipath TCP with a single subflow, and then it would behave like regular TCP. And if you need to upgrade it to use multiple subflows during the lifetime of the connection, this is fine. So you can create the second subflow at any time. If you want to only create the second subflow after 7 minutes, you can do that with the API. There is no issue with that. But you need to negotiate multipath TCP first.
Okay, thanks.
Right. Any more questions for Olivier? There's one.
Yeah. So Anna Brunström. So you talked about the option to control the stack and select various schedulers. So how fine-grained do you think this control, would it also be, for instance, possible for the application to say, I want to send the packet on a particular subflow, basically doing the scheduling at the application layer?
So when I mean controlling the scheduler, let's say you have a round-robin scheduler and the default RTT-based scheduler. The idea would be at the beginning of the connection, you specify which scheduler you would like to use for this particular connection. But then giving to the application the ability to specify for each data. So every time you do a send or maybe a send message to say this data must be sent over a specific subflow, I don't think we should do that, because if you force a specific data to be sent over a specific subflow, then you make it impossible for multipath TCP to retransmit the data over another subflow. All the semantics of the call becomes very vague. So I don't think that we should let the application specify over which path a given data will be sent. Maybe it's possible to send a hint saying it would be nice if the data could be sent over this subflow, but we cannot have a strong guarantee because you never know what will happen on the MPTCP stack, and the MPTCP stack needs to have the flexibility to switch from one path to another depending on the retransmission conditions, the congestion conditions, and so on, which is not exposed to the application. So I would avoid to give to the application developer the ability to specify a subflow for a given data. But maybe it would be useful to let the application developer change the scheduler during the lifetime of the connection. Mm-hmm. Which means that if you implement a priority scheduler, for example, you could say I have two subflows, the cellular and the Wi-Fi. At the beginning, the Wi-Fi is priority, and then over the connection, we switch the priority, which gives almost what you want to do. But I think this is cleaner from the MPTCP stack viewpoint, at least. Mm-hmm. And the semantics is clear of that. So starting at a given point in the data stream, then we switch the scheduler. But if you have a specific use case, talk to me offline and then we can discuss them.
Okay, so we're about out of time, so thank you very much. All right, thanks. Okay, so the next paper is multipath bonding at layer 3.
All these new faces up here, it's crazy.
Yeah, hello, my name is Mia Kühlewind, and I'm actually presenting this on behalf of our student who, of course, did most of the work and could not be here today. This is also joint work with Swisscom because that's their use case scenario, which I will explain very soon. I give you a quick overview. So first of all, I give you motivation of the scenario we've been looking at and what the specific requirements were we were trying to solve in the solution. Then I'm presenting the architecture and the scheduling algorithm to use multiple passes in our scenario. I talk a little bit about the implementation. I show you some evaluation results. There are more in the paper, and we also have more than in the paper. And I can conclude that it works for our scenario, and there are probably improvements because this is like a first step in the work. Okay, that's the scenario I'm talking about. And this is not only like we want to use multiple links. We have a specific scenario where, especially in Europe, this happens quite often, where you have a fixed line and it's there for quite a while and doesn't get updated because they don't invest in this. And so the capacity of your fixed line is actually rather low. At the same time, you probably have somewhere a new LTE system up because they actually invest in this part of the infrastructure. And specifically, your operator is not able to provide you certain services like a high quality streaming video service or some TV services because the fixed line just gives you not enough capacity. While the mobile capacity you have here is also in rural areas often not highly used, so you have much more capacity available here. And in this scenario, you would like to use both links and send data belonging to the same service basically over both links. Yeah, this is a complicated image, which is actually not that complicated. The solution we are looking at includes two proxies, one at the ingress and one at the egress. The customer side proxy can be in the CPE or somewhere close to the access link, and there's a second proxy further back in the operator's network. Of course, you can send data in two directions. That's why you have so many arrows here. But basically, both directions works the same. So if you look at one of them, it's enough. And in our scenario, usually we request some service like a video streaming where we have a server. Can I point here? Yeah. Where we have a server in the operator's network that sends a high amount of data to the client over this ingress gateway, over both of the links to the client. Here's an egress to the customer. And what we need to do in our solution is two things. In the ingress, we need to decide about the scheduling, which packet to send over which link. And at the egress, we do some reordering. And to be able to do this reordering, we assign a sequence number, proprietary sequence number to this packets.
Can I ask a
yeah.
quick clarifying question?
Sure.
So it looks like in this that the customer bonding gateway has a radio because it's talking directly to the LTE access. It's not using the radio in the device?
Yeah.
Thank you.
Yeah, and the other thing we're doing is we have to send some loss reports, at least for the DSL link, back to the scheduler, so the scheduler can decide, has some information about the congestion that happens on the DSL link and can decide to switch load over to the LTE. So what we do from the scheduling, and give you more details on the next slide, is we first send all the data over the fixed line because that's what we actually want to use. And when we see congestion, we send some data over the LTE link. Yeah. Just to make this point very sure, that's the scenario. First want to fill one link and then the other link, but that also makes our scheduler quite easy. So we use a round robin scheduler, and we start with a weight for the mobile link of 0, so no traffic over the mobile link, and we have a fixed weight for. Oh, sorry, that was the wrong button. We have a fixed weight for our landline link, and we just choose the random value, basically 50, and it doesn't really matter what you choose, it only influences the granularity, how to switch over traffic. For all the scenarios we present for our relation, we just use 50. And then we calculate the mobile weight based on the loss ratio we see. So this is the loss reports we get, and we also count the packets we have sent, the total number of packets. And we have this control parameter K here, which influences how quickly you react to something. And that was part of our study to evaluate what's the right parameter here for the scenario we've been looking at. There's a little addition here, because when you actually see that the fixed link got filled, you have to switch over quickly to the LTE. And to speed up this process, we have this additional scheme here. So if the weight is 0, no traffic on the mobile link, and we start seeing loss reports, we increase by the number of lost packets initially to just switch over more quickly to the mobile link. And then the other part is, if you see suddenly less traffic, you also want to move all the traffic back to the fixed line. And here we have first a waiting period of TDWD. So we just wait, and if we see for this time no loss on the fixed line, we start switching over. And then we have a time period of T report, 50 seconds. And for each of the reports we get where we don't see any new losses, we decrease by 1 our wait on the mobile line. Yeah, to give like on a high level a little bit more implementation details. So what we need to do on the Ingress side. So this is all implemented in a Debian system using NetFilter queues. And what we need to do on the Ingress side is we have 2 different kinds of packets. We have the data packets and we have the control packets that we get from the egress containing the loss reports. So if we see the loss reports, we extract the information and throw the packet away. If we have a data packet, we have to assign our own sequence number to it and decide about the scheduling. And in the scheduling, we just calculate the weight as described previously, make a scheduling decision, assign the right net filter mark and put it into the respective queue, and it gets sent out. And of course, we have to count the number of packets so we can actually do the calculation of the weight. For the reordering, it's like this is actually where all the complicated stuff happen, and it's also not super complicated. We try to actually design a mechanism that is as simple as possible. And there are 3 options. Either you receive a packet and it's just the next packet you have expected, so you can send it out, or you have you receive a packet and the sequence number is higher than the one you've expected, so you might have lost a packet or it's just delayed or whatever. So you put it into the reordering buffer and you wait for a certain time and to see if you still get the packet in the right order. Or the third option is you get a packet that has a lower sequence number than expected. That's the case where you probably already have decided that the packet is probably lost, and then there are 2 options. Either you just discard it because it might be too late, or you send it anyway and it's like, yeah, still might be too late.
Hi, I'm Stuart Sheriff from Apple. Very quick question. Is this for TCP traffic or UDP or both, because they're encapsulated? I mean, because I see you say UDP packets at the top there.
Yeah, sorry, I forgot this at the beginning. So where we started is actually wanted to make this possible for UDP traffic, because where Swisscom also started is that they've been looking at TCP solutions, and the first thing they've been looking at is actually MPTCP proxies that only works for TCP, or that only safely works for TCP. Because if you have UDP packets, you just don't know what's in the packet. And so we assume a UDP scenario here, and we also assume that we don't know if the traffic is reordering sensitive or not. So we just try to reorder to make sure there's nothing happening here. Was this a question, basically?
Yes. I assume because this is operating on datagrams, you could do this equally well for all IP packets, and it would work for TCP as well.
Yeah, so I mean, like we don't know what's inside the UDP packet. It could even be TCP inside the UDP packet, right? For our test scenarios, we actually only used a non-adaptive UDP traffic, and then we also had some TCP traffic, which we did not schedule as cross traffic. But yeah, also in our scenario, we were usually assuming like 1 flow, because that's like this big flow that doesn't fit on 1 link, and we need to schedule.
Thanks.
Okay, so in the reordering, there's 2 things. You receive new packets, you have to decide what to do with it, send it or buffer it. And then every time you send a packet, you also have to check your buffer and see if there's any packet that is now ready for send. That's the next one in order. Basically, that's the lower part here. Okay, so that's our evaluation scenario, and that's where I probably would have said what I just said, but I forgot to say this earlier. So we actually set up a test bed in the lab using Swisscom equipment, and we had the Swisscom router here and a real connection, DSL connection, and we had our own server sending packets here. And then the second connection was also using an LTE stick provided by Swisscom. In our scenario, we were always sending UDP data from the server to the client, and then we have a second evaluation scenario where we use just an external file server, we downloaded a big file using TCP also onto our client. So traffic is always flowing from here to there. Yeah, as I said, we've sent just dummy TCP packets, UDP packets in this case, equally sized. And we measured, to set the parameters initially, we measured the capacity of both of the links. So our fixed line had a capacity of 60 Mbits per second, no, 64 actually, a max capacity measured, and a delay of 13 milliseconds from the client to the server, or other way around. And the LTE stick provided usually around 60 Mbits per second and had a very varying delay, about 25 to 40 milliseconds. Okay, that's our results. Now, so that's like just a number of measurements where we have really just one UDP flow to, figure out how the basics of our algorithm works. What you see here is the two parameters we tested. So that's on the one hand, it's the K parameter where we have here K for 0.1, K for 0.5, and K equals 1. And then the other parameter we have is this waiting period until we move traffic back. And we also tried 3 different parameters. This is 50 milliseconds, 250 milliseconds, and 500 milliseconds. And what we did with the traffic is we started at a rate that would be just enough, or about enough to fill the fixed line. And then we increased our traffic until we had a rate of about like 105 Mbits per second, I guess. We stayed there for a while, and then we decreased the rate again to make sure how the mechanism works when you move it back from the LTE to the fixed line. And now you can just basically see the different behaviors of the parameters. So for example, if you have a low K value, it really takes, and the red line is the idle behavior. The blue line is the traffic we see on the DSL link, and the green line is the traffic we see on the mobile LTE link. So for low K values, you see that it's actually a little bit delayed, where we should here already have moved all the traffic. It takes a while, and we see a high loss rate, basically. And here as well, it's a little bit delayed. However, if you have a higher K value, it's just, more shaky, basically, because you're doing something the whole time. So this is like kind of a trade-off between responsibility and stability, basically. And then the second thing you probably want to look at is the loss rate. And like in all these scenarios, we have a rather high loss rate of more than, like here, more than 1%, but here it's even 4 to 6%, which is probably not acceptable for a deployment. And down here in the parameters, we have a lower loss rate around or underneath 1%. So that's probably where you want to go if you want to deploy this system. Okay, one more evaluation result, just as an example here. We also tried to use the system with TCP cross traffic. And basically, we had this one where we had, again, one UDP flow that is with different rates, actually, and then just downloading the file with TCP simultaneously. And as TCP is adaptive, it will just, take whatever it gets. The TCP traffic was only on the fixed line, while the UDP traffic could be moved to the mobile line as well. And we had this first scenario where the UDP traffic, which is the blue line, was not enough to fully fill the fixed line link. So in this scenario over here, the red line, which is the TCP traffic, still gets some capacity. But if the UDP traffic is actually able to fill the whole fixed line, we also, depending on the parameters we choose, maybe the TCP doesn't get any capacity at all. But depending on what your deployment scenario is and the service you offer as an operator, this actually might be what you want. Down here in the second scenario, we choose the much higher waiting time to move traffic back, which makes the reaction more slowly, but it's also basically more fair to TCP traffic because it's less aggressive. And in this scenario, you can actually see that it's also more shaky. But down here in the scenario where the UDP traffic would be able to fill the fixed line, we move a bit some traffic over to the mobile line, and so the TCP traffic gets some rate as well. And that's just to show, it depends on the configuration you take and what you want to provide to your customers. Yeah, so to conclude is we designed this mechanism for not only TCP, but also for UDP or all kinds of traffic. We tried to find actually a simple solution for the specific scenario where you want to fill the fixed line first and then move over traffic to the mobile line if needed. We we did on the ingress, we do two things. We do the packet mangling by assigning a sequence number and the scheduling, and on the egress, we do reordering to make sure that the traffic underneath doesn't get problems because packets are not ordered. Of course, this introduces delay, but that's, you know, that's you have what you have to take if you want to use a mobile link. We showed in our evaluation what you can do with these parameters, but it really depends on the scenario you want to use it and the goals you want to reach. So there's no recommendation for like the best set of parameters here. And we try to further work on this. So one question we have is, first of all, how does this scenario look like if you have real traffic and not only dummy traffic? If it interacts with the application, how would it look like if you have also MPTCP traffic in parallel? So TCP is also using both of the links. Would this still work, or would this be kind of unstable, or like traffic would be moved forth and back all the time? And then what's also very interesting for our research is a way to figure out if the UDP traffic is actually reordering sensitive. Because if it's not reordering sensitive, you could just shut off the reordering and save a little bit of latency and improve the system. Thank you.
Hi, I'm Dirk Kutscher. So I took it as like the whole motivation for this was that you didn't want to tunnel loss tolerant traffic over multipass TCP. So that's why you came up with your own approach. But
it's not only loss tolerant traffic. It's first of all, usually the solutions you can buy today only works for TCP traffic because it's a real TCP proxy. It finishes your TCP connection, starts a multipass TCP connection, then starts a new TCP connection again. So it really doesn't work for UDP. And then tunneling UDP inside TCP might mean, because usually even the UDP traffic is congestion controlled. So you have like 2 loops of congestion control in there, and that's like nothing I would recommend here.
right, that's what I just said. But did you, I mean, in theory, you could still build this. Did you actually compare the performance of your approach to a, say, UDP in multipass TCP tunneling approach? Because you could build both systems.
No, so I mean, we talked about it. We didn't compare the performance, but it's also really risk you're taking. Like for us, we know that our traffic is not adaptive, but if you don't know that, I would just not recommend you that solution. But it's we discussed it, and it's kind of still on our list. It's not the first priority because there are other things we didn't investigate so far, and we just didn't have time anymore to do it.
Hi, Paul Evans from Boosty. I completely agree with the layer 3 approach, spot on. Also, the cheapest pipe first in the real world. I think, you know, when we were talking about the KT example, you know, you've got 500 megabits Wi-Fi and 500 megabits LTE. Who actually needs that? The real world needs, you know, I want to look at this web page. I want to find the cheapest way of getting the experience I want. So going for cheapest pipe, absolutely correct. We've launched a solution for the home, doing something very similar, and also for iOS and Android devices. We've launched a little Boosty router, sale in the UK, and it allows you to do just that. But one of the other points, I think, is the very first question was, how do you actually use cellular? So again, rather than having into the gateway a built-in LTE or 3G modem, we've got this little smartphone app that sits on here that's discovered over the LAN and basically allowing people to use what they've already got for. Because the one thing I think you guys have absolutely done right is trying to look at what's the real world application and constraints. And it's people don't want to suck as much data down both pipes. They don't want that necessarily, because it's going to cost them real money. The operators don't necessarily want that. So I think it was a great presentation. Thank you.
Thank you. I mean, the scenario we had was slightly different because it's really a service provided by the operator in our case, but it's probably applicable. But I mean, I want to say there are a lot of scheduling algorithms, and they have tons of parameters, and probably you can also use those mechanisms to tune them the way you want them to have. But they are just complicated because they are like general purpose mechanisms, and we just try to do something very simple because we know the scenario, and so we could do it.
Hi, Stuart Cheshire again. You kind of suggested at the start, without going into details, that this was targeted at a very specific product offering. It sounds like video distribution to the home, kind of cable TV replacement. And given that very constrained nature, rather than waiting for packet loss, if you know the customer has a 64 megabit DSL line, can you not simply model that they have 64 megabits and send less than that so you don't get lost?
So I mean, like actually, we work with the research department. So they don't have a specific product in mind yet, but they know what the products are and try to apply to the current products. But anyway, this is like if you really know that you want to use the whole link just for this one service, that's okay. But if you also want to allow TCP traffic at the same time and whatever, and there might be other traffic, then that's probably not what you want. Then it's getting more complicated because you don't know the other traffic demands.
Okay.
Also true.
Jörg, so this seems to be a bit of the opposite that people have been doing in many occasions where they try to do offloading from the cellular network. At times when my home DSL line is highly loaded, I suspect this would also apply to my neighbors. So this seems like a perfect solution if I'm the only one deploying it in my neighborhood. So, but if all of us are starting to do this and say, well, Wi-Fi here sucks, let's combine this with cellular. So how far do you think you can stretch that?
Brian wants to answer this. I want to add one point. So the scenario is not the DSL is overloaded. The scenario is the DSL just doesn't provide enough capacity for the service we want to provide.
Which is roughly the same thing.
And it's not roughly the same thing because we are talking about scenarios where you're in rural areas and there's like one house somewhere in the middle of nowhere, maybe not one house, but a few houses. So there's actually not a lot of traffic demand. It's really the link capacity that is a problem here.
So there's kind of a perfect storm of this making sense that happens in a lot of areas of Switzerland, where up in the mountains, so about half of the area where there are settlements in Switzerland is people in long linear valleys. And it's very difficult to think of a topology that is worse for DSL, right? So you'll have people that have kilobit DSL lines, like multiple kilobit DSL lines, but you're not quite at the megabit limit. And they live really, really close to large skiing arenas and hiking areas where you need to build the LTE network to handle everybody who's flying over for the weekend. And during the week, it's basically idle. Right, so there's like one other country in the world that has this topology. It's the Japanese Alps. I get you could also do it in the Southern Alps, and you could. No, but they have fiber. Right, yeah. Right. See, that's the problem. This would have been really interesting in Japan about 10 years ago. But the idea is, Swisscom's looking at, okay, well, we'd like to be able to offer TV here, but there's no way we're going to be able to do that other than for the first 5 people up the road on DSL. So
you can watch TV unless there's weekend and vacations.
Yes, but on those days they're up skiing. Why would you watch TV when you could do skiing?
No, so this is a very specific scenario, which is a problem. But there are also other areas where they invested the money in providing mobile capacity and not in providing the fixed line capacity. So there's a lot of unused mobile capacity there.
Yeah, so where we're seeing the demand is actually in places like central London for our solution. Kid you not, because there's no cabinets for fibers to the cabinet in a lot of areas. So a lot of people are stuck on ADSL 2+ long loop lengths because there's no little green cabinets to do VDSL. Also, we're finding with the operators that we're working with that actually adding more cellular capacity is a darn sight easier than digging up the road, deploying fiber to the premises. So yes, the previous question was absolutely right. Yeah, you might have lots of people using the cellular, as long as you're efficiently only using cellular when you need to, then actually it's an awful lot easier to stick up a new mast than digging up the roads and putting FTTH.
Thank you very much.
Okay, thank you. All right, so we have 2 short papers to finish. The first is the multipath TCP aware load balancer, and the second is multi-homing on a single link. So again, a reminder that these are 5 minutes, no questions, and if the person is still talking after 5 minutes, we will start clapping, and you should all join in until the person stops talking. Go.
While he's setting up, so we have a big roll of tape that has appeared now. I think it's in the back somewhere for the people that want to put up their posters in the break. We're also trying to get some cardboard thingies to make these easels a little bit more functional. But maybe try and see if the tape helps you. If not, then I'll chase the secretariat in the break and see if they've done anything for us in the meantime. First one to put up a poster gets to pick the best easel. All right, I'm going to start your time. 3, 2, 1, go.
So I'm Simon from University of Liège, and our poster title is towards multipass TCP load balancer. So as we previously seen in the other presentation, multipass TCP enables two peers to communicate with multiple subflows. And these subflows are regular TCP connection. There are multiple advantages that were already presented. We focus in your work on the case of load balancer that will spread connection between several servers. And when a client wants to connect to a particular server, to the server, the first subflow will be balanced to a particular servers, but the second subflow, that is another TCP connection, will be balanced to a completely different server because the subflows are different 5 tuples. And hence, you cannot use multipass TCP in this scheme. So we proposed a solution that is a load balancer that is multipass TCP aware. And what do we do? When the first subflow reaches the load balancer will track the cryptographic materials that are exchanged between the client and the server in the MB-capable option. And the load balancer will compute the token of the server. And when the second subflow will reach the load balancer, the load balancer will be able to identify the second subflow as belonging to the previously seen MPTCP connection. And with that solution, the server and the clients can communicate thanks to multipass TCP. Our solution is quite simple, and we provided a proof of concept with a very simple topology, but it does not need any modification of multipass TCP, and we do not need no hack or previously TCP behaviors, etc. On the other hand, it's a stateful solution because the load balancer has to remember the token of the server and some other things. And we provided the solution with a unique load balancer topology, but we have ideas to cope with the case of multiple parallel load balancer at the entrance of the server cluster. But if you're interested in your work, you can come discuss on the poster. Thank you.
3 minutes. That was good. Next one.
Next one
is
multi-homing on a single link.
Right button and you have to close the window. Here's the red thing. So does it still work?
Hey, this is Philip Teasel from TU Berlin, and this is mostly the work of my master student Bernd May. There are a lot of companies outside or other users outside that want to become multi-home. So they just want to get multiple uplinks But they don't want to run BGP because it's too complicated or too expensive to get the whole setup. So we looked at a different approach and just using multiple IPv6 prefixes for each upstream. The nice thing about this is with one IPv6 prefix per internet access, you get an end-to-end solution, and it's completely transparent. So you can make it application aware if you are doing the flow scheduling right at the client. So there are two things to look about that. First thing is, how can you auto-configure it? So if you're at the home network or the company network, you can't just statically configure all client machines. The protocols for IPv6, there are status auto configuration and DHCP-v6. They slightly differ in how usable they are for this scenario. So with status auto configuration, your can have a decentralized operation. So each router is sending the router advertisements compared to DHCP-v6, where you just have a single DHCP-v6 server. So if you want to have this scenario in a case where you have multiple uplinks, you just need to have one central point where all configuration is done for DHCP-v6, whether you can just do it spread over the different kinds of routers for DHCP, for status auto configuration. And this makes status auto configuration feasible for opportunistic bandwidth sharing options like you, for example, presented with the idea of a little box or just using the cell phone as an additional router to get more home bandwidth. Whether for DHCP-v6, this would involve a lot of complicated negotiating between the devices. Finally, if we are looking at the client support, what's out there, you see there's a limited client support for status auto configuration, and there's no client support for DHCP-v6 with multiple prefixes. And basically what we did was extending DHCP-CD to completely enable this auto configuration case and make it possible to auto configure a client that can instantly use multipass TCP or our framework socket intents that does flow scheduling in a way that you can just plug in the machine and use the multiple uplinks of the network. Finally, if we want to do this, we get a little issue, especially with DNS, because CDNs and other big sites are doing topology optimizations of their server mapping based on DNS. So if you take the DNS replies for one uplink and use it on the other uplink, you might have a suboptimal or even unreachable endpoint for your connection setup for fetching your objects. And you have to care about that. So for a few things how to do this. First, DNS replies have to be kept separate per prefix. And also the DNS queries need to be mapped to the right prefix. So either you do this by having multiple DNS servers and have multiple different resolver configurations on the end host, which is quite complicated to do, or you do this by using eDNS 0 client subnet extensions and hope that this works with a single client. But still, if you're doing a DNS caching on the client, you have to keep the source address and map with the source addresses to the right DNS replies when caching, which makes this a little bit complicated. We have some more details about our Linux implementation for DHCP-CD on the poster, and therefore, thank you.
20 seconds to spare, perfect timing. All right, so thank you very much. That was the end of the first session. We have a break until 10:45 now. And if the presenters, if you send us your slides, we will put them up on the website. If you don't want them on the website, don't send us your slides. Thank you. There should be coffee at the back.